Now,
Happy to have Burgos Gil, who is going to talk on high patterns and mixed course.
okay, so thank you very much for inviting me to Cambridge and for organizing this very nice semester. So I want to talk about this higher Hain pairing, so a Hain pairing between higher cycles, and this is joint work with Goswami and Pearlstein, that both are in Texas A&M University. So let me start explaining a little bit about the classical Hain pairing, or the classical Archimedean component of the Hain pairing. So we start with X as smooth projective variety, let's say over the complex numbers, and let D be the dimension of the variety. And then we pick up two algebraic cycles, Y and Z, and they have Y has codimension P, Z has codimension Q, and now we assume that the sum of the codimensions, P plus Q, is one more than the dimension. So if they are in general position, this means that they don't meet. So we will assume that they don't meet. And now we want to define some invariant that tell us something about the position of these two cycles. So the topological intuition is that this number should be something like the linking number. So when we have two cycles that don't meet, the number of turns that one cycle turns around the other is the linking number of the two cycles, and in some sense this is an algebraic version of this number. Now, in order to construct this Archimedean component of the green current of the cycles, we have to take two what is called green currents, Gy and Gz. These green currents means that they are some kind of primitives for the cycle. Yeah. So we have these two cycles, Y and Z. Then the cohomology class of the cycle are represented by the current integration along the cycle, and then this green current is something that bounds this current that can be seen as a singular differential form and a smooth differential form. So then I take a differential form, G of Y, that will have singularities along the cycle Y, and I ask that this second order differential operator, ddc of Gy, plus the current integration along Y, has to be equal to a smooth function, a smooth form omega y. Then Gillet and Soulet develop a whole machinery of the star product of these objects, and they define the star product of Gy and Gz by this formula. So we take the current integration along Y multiplied by G of Z plus the current G of Y multiplied by the smooth part of the other one. It turns out that even if this looks antisymmetric, it is well defined up to the image of delta plus the image of delta bar, and this product is associative and commutative. So in particular, it doesn't matter if we start with the current integration on Y multiplied by Gz and then Gy multiplied by omega Z. We can also construct this product, taking here omega Y multiplied by Gz and then here Gy multiplied by delta Z. And one thing is important is that here I am multiplying two currents. In order to be able to do this product, one has to be careful and represent this object by a differential form with singularities, and then one can define this product in this. Okay, now this product, of course, this depends on the choice of Gy and Gz. Now, if we add another condition, so we assume that the class of the cycle Y, this is a class that lives in a Hodge homology of degree 2p of x, and the class of Z that will live in the Hodge homology on degree 2q of x, these classes. Now I assume that these classes are 0. Then it turns out that this integral does not depend on the choice of Gy and Gz, and only depends on the choice of Y and Z. Now if we go back to this analogy I was telling you about this linking number of cycles, if the class of Y is 0, I can impose that omega Y is equal to 0. And then I can take a form Gy that will be really a boundary, so a form that bounds delta Y. And then the product will be just, I take the form g of y that bounds delta of, or g of z that bounds delta of z, and I multiply by delta of y. Now, if you think on cycles, if I want to look at the linking number of the cycles, what should I do? I should fill one of the cycles by a disk, and I just have to look at how many times the other disk intersects this disk. So exactly the same formula I will get. Okay, so now this is the Hain pairing, and in particular we obtain a well-defined pairing of pairs y and z, such that the intersection of these two elements is empty, but that they are homologically trivial. So I can only have a well-defined pairing if I take these two cycles that are homologically trivial, and this will give me a real number. Now, the first observation is that this pairing, as it is defined, does not descend to the Chow group. So this is something that only is defined for cycles. So I cannot define this in the Chow group. But if I assume that everything is defined over Q instead of being just complex, then I can add finite components, and then I can have some kind of complete Hain pairing that this is well defined on the Chow groups, not just on cycles, but really on the Chow groups. This is thanks to the proper formula. And an example of what kind of numbers do we get. So if we start with the basic one, so I take x equal to p1, y will be just 2 points, z will be another 2 points. Then the invariant one can associate to 4 points in p1 is just the cross ratio of these 4 points. Then the Hain pairing, this Archimedean component of the Hain pairing, is given by taking the cross ratio of these 4 points, then the logarithm of this cross ratio, and then some signs, and some normalization factor depending on the choices you have. Okay. Now, so this is in some sense a Hain pairing that is defined using this product. The question is whether we can interpret this in terms of Hodge structures. Okay, for this we will look at biextensions. But before going to the biextensions, we first need to understand a little bit better the class of the cycle, or what we can do with the class of the cycle. So I consider this exact sequence. So I have here on all my talk, cohomology will denote Hodge cohomology. So the cohomology with coefficients in Z with its Hodge structure. Now here I have the cohomology of X with support on the cycle Y. Then there is, of course, a map of forgetting support that goes to the cohomology of X. And here I have the cohomology of the complement of Y. Then I have, again, the cohomology of X in degree 1s. Now, I know that the group here, if we continue the exact sequence, this group here will be the H2P minus 1 with supports on Y. Y has codimension 2P. Then semi-purity tells me that the group here will be 0. So this map is injected. Now, I was assuming that X was smooth and projective. So this is pure of weight 2P minus 1. This part here will be the Hodge, the cohomology of an open variety. So in general, it will be a mixed Hodge structure. But this one is again pure. But this case is pure of weight 2P, and it continues like this. Now I have the class of the cycle Y, and one can obtain a refined class, not just the class on X, but I can obtain a refined class that lives in the cohomology of X with support of Y. And the condition that the class is 0 means that this class here goes to 0 in this group. So what I can do now is take the pullback of this sequence with respect to this class, and then I can name this object H just to short the notation, and I can twist everything by the Tate mixed Hodge structure set of P, and I get an extension of this shape. So here this will be the the basic mixed Hodge structure set of 0. This is the extension I am getting, and this will be the cohomology of X, but twisted by P to put it on weight minus 1. I am just moving the weight from here is 2P minus 1. I am multiplying by a mixed Hodge structure of degree of weight minus 2P to get weight minus 1, and I get this extension. So this is an element, is an extension of Z and H of P. And the class of this extension is exactly the Abel-Jacobi class of the cycle Y. Okay. Dually, we can do the same with Z. So if I take Z, I will get an exact sequence like this one. But in this case, instead of having the cohomology H2P minus 1 of X, I will have the cohomology H2Q minus 1 of X. But then I can dualize this short exact sequence, and I can get an extension of this chain. So the dual extension is to Z, then Z will be in the left of the sequence, and then I will have the cohomology of X, but in this case, H2Q minus 1 twisted by Q dual. But now, using Poincare duality, and using the assumption that P plus Q is equal to P plus 1, the cohomology H2Q minus 1 of X twisted by Q dual is exactly the same as the cohomology H2P minus 1 of X twisted in this case by P minus 1. So this is the H we had before, but in this case twisted by P minus 1. So if I twist by 1 just to get exactly the same Hodge structure I had before, a Hodge structure of weight minus 1, then I obtain this dual sequence here. So the class Z extension of Z, dual, twisted by 1, then again the same pure Hodge structure of weight minus 1, but now I get on the left the mixed Hodge structure of weight exactly minus 2. So this will be an element on H1 of HP Z1. And this will be the dual class of Z. So this is again the Abel-Jacobi class of Z. And now I want to glue together these two classes to get a B extension. So I have an extension on one side, an extension on the other side, and I want to get a B extension on both sides. The point is that I cannot glue together just, so if I take two extensions, there are many ways to glue them. So I need to glue them in a way that is prescribed by the geometry. And in order to do that, what I consider, so if I want to glue these two guys, what I can do is to consider a very big commutative diagram. Okay, so this is a complicated diagram, but you can see here, this is exactly the exact sequence we use to define the extension of Y. So I have the cohomology of the complement of Y, I have the cohomology of X with support on Y, I have the cohomology of X, and then I have this zero that comes from and the exact sequence will continue in this direction. The one that is here is exactly the dual of this one applied to Z. So instead of considering the cohomology of the complement of Z, I am looking at the cohomology of X relative to Z. And then I have here the cohomology of Z. Then now the exact sequence continues in this direction, but I know that the group that comes here, this will be the cohomology of Z in degree 2p minus 1. But now by dimension reasons, this will be 0, because by this condition on the codimension, I know that the dimension of Z is exactly p minus 1. So the group here will be 0. Okay, so I have these two lines, we understand these two lines, and then once we have fixed these two lines, then there's a question of fill completely the diagram. So this element here will be exactly the cohomology of the complement of Y relative to Z. Then the element that has to be here is exactly the cohomology of the complement of Y in Z. Here, this will be the cohomology on with support on the intersection. Here is the cohomology with support on Y, but relative to Z. And so this is just completing the square once we have fixed this to this row and this row and this. Okay. But now, what do we know about this diagram? So the first thing that we know is that by assumption, the intersection of Y and Z is empty. So this corner here is 0. Since this corner here is 0, I know that these two guys are the same. These two guys are also the same. And then my diagram is a diagram like this. But now, remember that I have here the class of Y. And I can take the pullback of everything with respect to the class of Y. And here the class of Z will give me a map of this guy to pure thick. So I can take the push out of this part of the diagram with the class of Z. Okay, so we twist by Z of P, we take the pull back by the class of Y, we take the push out by the class of Z, and then the diagram we obtain is something like this. So in this line, we obtain exactly the extension associated to Y. In this column, we obtain exactly the dual of the extension associated to Z twisted by 1. Then here we have a 0, and then we will obtain something in the middle, a mixed Hodge structure in the middle, that contains in particular the dual of this extension, and it projects on this extension here. Okay. Now remember that in the corners we have pure mixed Hodge structure. This one has pure weight -1, this one has pure weight 0, and this one has weight -2. So I have a mixed Hodge structure with 3 steps, like this. So this B, Y, and Z is a mixed Hodge structure with weights -2, -1, and 0. And if I look at the graded group associated to this mixed Hodge structure, the grading is as follows. I have on weight 0, I just have the trivial Tate structure set of 0. In weight -2, I have the Tate structure set of 1. And in weight -1, I have the cohomology of X on degree 2p - 1 by twisted by p to put it in weight 1. So this is the class of the extension. And now I want to look at what are the possible biextensions of this shape. There is a classification of biextension of this shape, and this is what will give us the interpretation of the Archimedean part of the Hain. So the next theorem is due to Carlson, and it appears in a paper of Hain, but at least in the paper of Hain, it claims that this was also done by Bloch at the beginning, but at the end the paper was only written by Hain. So let H be a mixed Hodge structure of weight exactly -1. Then, if I look now at the extensions, but not over the integers, I look at the extensions over the reals. So the extensions of real mixed Hodge structure of the trivial structure R by H, or I look at the extensions of real mixed Hodge structure of H by R1, these are always 0. So there is no non-trivial extensions when the distance is only 1. So extension between two real mixed Hodge structures that differs on 1 is always 0. So this means that this extension, once we tensor with R, and these extensions, once we tensor with R, they are split. Then the second part is that if now I look at all possible mixed Hodge structure with weights -2, -1, and 0, that satisfies the condition I had before, so that the graded part of weight -2 is exactly R of 1. The graded part of weight 0 is exactly equal to R. And the graded part of weight -1 is the fixed one, H, now tensor with R. This group here is isomorphic to R. This is, so it's classified just but one real number. Okay, this part, 1 and 2, is Carlson's theorem because he has a general way to describe extensions of mixed Hodge structures, and applying Carlson's formula, we get these two things. And then the theorem by Hain tells us that the class of this biextension is exactly the Archimedean part of the Hain. So the Archimedean part of the Hain can be interpreted as the class of this biextension. So how this works, for instance, this isomorphic with R. So one way to describe this isomorphism is using what is called the linear splitting. So if I have a mixed Hodge structure defined over the reals, then there is a unique splitting of M as a direct sum of pieces of type PQ that satisfies the following properties. The first one is that the Hodge filtration is compatible with this relative. So the part Fp of the mixed Hodge structure M is just the sum for all possible P prime bigger or equal than P of M P prime. Then the weight is also compatible with the degree. So the Wn part of M is just the sum for all possible pairs PQ, such that the sum P plus Q is more or equal than N of M PQ. So for the moment, this looks like I am describing a split mixed Hodge structure, but now here it comes the point is that the degrading is not compatible with complex conjugation. So if I take the complex conjugate part of this NPQ, instead of getting NQP, I get NQP up to things of lower weight, let's say, but lower weight of a very complete shape. So I have that this conjugate part is contained in NQP plus the sum for all P strictly smaller than P prime strictly smaller than P, and Q prime strictly smaller than Q of this M Q prime P prime. In some sense, this explains why, if the difference is only one, it is always split over the real numbers, because observe that every M Q prime P prime appearing in the sum will have weight at least 2 below the weight here, because P has to be one less, P prime has to be one less than P, Q prime has to be one less than Q, so the error here will always has at least 2 weights below. So this explains why when there is only one difference over R, it will be split. Okay. Now a real mixed structure is split if and only if the splitting is compatible with the complex structure. Now I can look, okay, how can I cook an invariant that tells me when the B extension will also be split? Well, what I can do is to take an element, X, an element of the part of B degree 0, 0, not a real generator, an integral generator is what I have to take. And now, if I choose an integral generator, I can look at the conjugate. Now, the conjugate will live in B00 YZ plus the error term that will live in this B11 of YZ. Now, since I am taking an real or real integral generator, what I know is that this X, at least here, will agree with X. So if I take the difference, X minus X bar, the 0, 0 part will vanish, and I will get an element that will live in B11 of YR. And it will be either real or imaginary, depending of if you are looking at the Betti conjugation or the RAM conjugation. And this is exactly the class of the B extension. So the B extension is just classified by this device. So this is the invariant that tells us what is the class of the B extension, and this is the invariant that agrees with the Hain. Questions up to now? Okay, so this is the classical picture, and what we want to do now is to go to the higher two groups and try to define some kind of high pairing between higher cycles, and try to give an interpretation of this high pairing as an extension of mixed Hodge structure. This is more or less the plan. Okay, so for this, I have first to describe a little bit how the higher two groups are constructed, and I will explain the cubical version. So I denote by the square, P1 minus 1. And then square to the n will be just the product of the square n times. So this is P1 to the minus 1 to the n. And I have phases that goes from the square to the n to the square to the n plus 1. For I equal to 1 up to n plus 1, and for j equal to 0 or infinity, so the phase delta ij of t1 up to tn is just inserting j in the position I. This j can be 0 or infinity. So recall that here I am taking the square, it's just the affine line, but instead of the affine line seen as the projective space minus infinity, no, I am taking the projective line minus 1. So the points 0 and infinity are inside the square. Okay, and now I can look at the cycles, set p x n, so the cycles of codimension p in x cross the square n. That intersects all the faces of the square n properly. And these two zeros here means that I am looking at the normalized set complex. This means that if I look at the intersection as the pullback with respect to this face of set, this has to be 0 for all faces except one. The face where I is equal to 1, so the first one, and j is equal to 0. This means that I am including the square in the first component with component 0. And then there is a differential operator, a d, a boundary, that goes from cpxn to cpxn-1, which is given by just taking the pullback from the only possible face that remains. So I am asking that all the faces go to 0, and then I have just one remaining, and then I can define a boundary just taking the pullback. Okay. Now, then Bloch defined originally the simplicial version of the two groups, and later he also defined this cubical version. No, Levin also defined it at the same time, or who defined the cubical version?
I mean, it was actually Eilenberg or Simon Blaine who defined cubical homology, and then it really wasn't rocket science. I mean, the problem really was that the multiplication was difficult.
Exactly. Since we want to make multiplication, this is why we are taking the cubical version, because multiplication is easier, if you say. Okay? And the important thing is that this is a model of what is called motivic homology of the variety. Okay, so these are the groups.
You forgot to divide by degenerate.
No? Because
No, it's normalized.
I am taking the double normalized one.
Yes.
This is one of the good things of this, that I don't need to
Yeah.
divide by the degenerate, because I am taking the double normalized ones. Okay, and now one has to define what will be the analog of a green form or a green function on this set. Okay, now I look at my cycle y is a cycle of codimension p on x times delta n 0, 0, and I am assuming also that d of y is equal to 0. Okay, we put together all the conditions. This implies that when I restrict to all the faces, this will be 0. Okay? And then I can look at the class of y in the cohomology 2 pi or with support on y of x cross delta n, but relative to the boundary, because since I know that all the restrictions to the boundary will go to 0, then this y gives me an element on this relative cohomology, not just on the cohomology of x cross square n, but on the relative cohomology of this with respect to the x. Okay. Now, before telling something about this class, I can observe that in P1 to the n, I have two simple normal crossing divisors that are distinguished. One, I will call it an, which is just all the elements in P1 to the n such that one coordinate is equal to 1. So a square to the power n is just P1 to the power n minus an. It's the complement of an. But then I also have a second simple normal crossing divisor, Bn, that is just the collection of all possible T1 up to Tn, such that at least one of the coordinates is either 0 or infinity. So this is just the union of all the faces. So this is what is missing in a square to the n, and this is exactly the boundary of a square to the n. Okay? But now I can write two relative objects. So these two bars means that it is not really a scheme, but it's a relative scheme. A square to the n will be just P1 to the n minus an relative to Bn. And Gm to the n will be P1 to the n minus Bn, but now relative to an. It turns out that these two pairs are in duality, because you see, I am taking here the complement with respect to an relative to Bn, here I am taking the complement with respect to Bn relative to an. And these spaces have the property that the cohomology is concentrated in just one spot. So the cohomology IHR of a square n, this relative square n, is 0 almost always except in dimension n, when it is equal to 7. While the cohomology of this Gm to the n, this relative Gm, is 0 always except when r is equal to n, that I have the Hodge structure of weight 2n and pure type nn. So I have this cohomology. And I know that the ramp generator of this Hn of Gmn is given by this differential form, dt1 over t1, which conjugates dtn over t. And in particular, using this differential form, I know that there is for every x, I have an isomorphism from hr of x cross delta n to hr minus n of x, which is given by the formula for to every omega, I just take the integral with respect to the P1 to the m of omega, which the generator of Gm. Observe that here I am using the duality between the square n and the Gn, because I am using a generator of the cohomology of Gm to construct a map to get rid of the square n. Okay, so the fact that square n and Gm are in duality is what explains why this explicit map gives me an isomorphism between these two guys. And in particular, if X is projective, this cohomology in degree R is pure of weight R minus n. So it's not pure of degree R, but it's pure of degree R minus n. Okay. And similarly, I have that HR of X cross Gm to the n is isomorphic to HR minus n of X, but now with a twist. So here the isomorphism is without a twist, but here I have to twist the things because the cohomology of Gn is not pure of weight 0, but is pure of some higher weight. Okay. Now, in particular, I know that HR of X cross square to the n is pure of weight R minus n. This implies in particular that if I look at the class of the cycle Y, which is the same, the class of the current integration along Y, in H2p minus 1 of X cross square n, it has to be 0. Later I will explain why, but this class always has to be 0. Now, playing around with the types of the different mixed Hodge structure that appears, one can prove that one can find differential forms as follows. So, a differential form Gy that is of pure type p minus 1, p minus 1 as differential form, and has singularities on Y and on AN. A differential form eta Y that has Hodge type P, so it's in the P part of the filtration, the Hodge filtration of differential form on X equals P1, and also has singularities on Y union AN, and a differential form theta Y, but now instead of being in the part FP part, it's in the FP minus N part of this homology, and has only singularities on AN, not singularities on Y. Okay? So the fact that this theta Y belongs here is related to this change in weight. And this differential form satisfies the following relations. The first one is that the derivative of the current associated to this differential form eta Y is exactly the current integration along Y. Okay? This comes from the fact that delta Y was exact. The class of Y is 0 in comparison with 0. The differential of Gy is up to some factor 2 pi I is eta Y minus eta bar Y, so the complex conjugate of eta Y minus eta Y, plus this smooth part here. And I also have some properties that the fact that theta Y is purely imaginary, and as differential form, the differential of this is 0, and here the Gy is real. Okay. I have to say something about this complex conjugation here, is that in this business, complex conjugation is a little bit tricky, because, well, not tricky, so there are two possible choices, in the sense that you have always a mixed Hodge structure. This means that you have the Betti cohomology inside the cohomology, and you imagine that the Betti cohomology is giving you the integral structure, so the conjugation is with respect to the Betti cohomology. And on the other hand, these are differential forms, and you can take just the complex conjugation as differential forms. So these two complex conjugations in general do not agree. This is why, for instance, the Betti part can be just R of 1. It will be imaginary. Here, when I put complex conjugation, I mean always the complex conjugation that respects the Betti part. Because if not, I have to add a minus 1 to the P in every. Okay? So which means that this guy is not in the Betti part, but in the anti-Betti part, while this one is in the Betti part. Okay? And Gy will be called a green form for this cycle 1 in this construction. Okay? Now, why I was saying that the class of Y has to be 0. So the point of the class of Y, since I can represent the class of Y by the integration with respect to Y, and this is in the FP part of the cohomology, and is also invariant under complex conjugation, this means that the class of Y belongs to the FP part intersected with the FP part bar of the cohomology. But this guy is pure of weight 2p minus n. This means that this intersection is empty. Hence, this class is 0. So this is how we know that this class has to be 0 in this cohomology, just by way it goes. The second point is that in this construction that I have made before, if I look at this theta y, this theta y defines a class in the cohomology H2p minus 1 of x cross square n. But I was choosing it in fp minus n because I can take the quotient with respect to fp, and I can take also the quotient with respect to the Betty part, which is rp, and this quotient is exactly what is called the limit cohomology of x on degree 2p minus n. And one can check that the class of this theta is exactly the regulator, the real regulator of y. So it's the class of y in this cohomology. So the point is that when we are looking at higher cycles, the ordinary cohomology class is always trivial. The class that is interesting is the class in this group, which is some kind of reference class, the image of the regulator. Okay. Now, how we can now define the Archimedean component of the Hain pairing? Well, we can do as before. We have this cycle y in of codimension p on x cross square to the n 0 0 set of codimension q in x cross square m 0 0, and I also assume that they are really cycles. This means that then that all intersections will be 0. Now I add the condition. So the analog condition that the p plus q is equal to d plus 1 has to be that 2 times p plus q minus d minus 1 is exactly equal to n plus m. Observe that when n and m are 0, I get exactly the condition I had in the classical case. Then the second condition that I will ask is that p1 upper star of y and p2 upper star of z. Now p1 is the projection of x cross delta square n square m just to x cross square n, and the second projection will be to x cross square n. Then I can pull back y to this space, and I can pull back z to this square, and I ask that these two guys intersect. Now, there is the problem is that now proper intersection no longer means empty intersection because of this condition here. So it's not true that this guy will have empty intersection in this space. But then I also have to ask for the condition that the regulator of y and the regulator of z is equal to 0. So in the classical case, we have that the class of y and the class of z were not trivial, and we had to ask them to be 0 to be able to get a Hain pairing that was independent on the choice of the increments. Here we know that the class of y and the class of z are 0, but then we need to ask that the regulator are 0 to get something that is independent on the choice of the being currents we have done. Now, for simplicity, I will just consider the case when n is equal to m equal to 1 for the discussion. And now I will choose green forms, gy and gz, green forms for y and z. And in order to fix them, I impose the condition that theta y and theta z are both 0. I can do that because I was assuming that the regulator was 0. So I can find these forms, gy and gz, satisfying this condition. And then the Archimedean component of the Hain pairing will be a normalization factor with 2 pi i's factors and so on of the product gy times delta z. Observe that this is exactly the same object that appears in the Gilles-Soulet definition of the same product. But the problem is that now I am not living on x, I am living on x cross t1 squared. So I have to add dt1 over t1 for the first variable and dt2 bar over t2 bar. So this will be a differential form, living on x cross p1 to the square, and I take this integral. So if I don't have n equal to m equal to 1, then I will have to plug here a more complicated differential form. And just make a sanity check. So G1 was a form of type p minus 1, p minus 1. Delta z is the coordinate integration along z, so it has b degree q. I am multiplying by this that has b degree 1, 1. So now if I add this, I get p plus q. But if I look at the condition of p plus q, and using the fact that n plus n is equal to 1, this is, oh, no, this is an error. So this is d plus 2, d plus 2. So the sum, which is exactly, the d plus 2 is exactly the dimension of this guy. Okay. Now, the point is that, so this is just a particular case of a whole theory. So we have developed a whole theory of...
Sorry, can you go back to the previous...
Yes.
have some question about
Yes.
your addition. Oh, I said D plus, oh, okay, yeah, no.
Yeah, so this is an error here. This has to be d plus 2, d plus 2. So I get 2d plus 4, and then I just will copy it. Yeah. Okay, so
What is the reciprocity property?
what do you,
You interchange y and z.
it's symmetric.
Symmetric or is?
Yes. It's symmetric taking into account the degrees.
Right. Right,
Yeah.
okay.
Well, I think in this case, since n is equal to n equal to 1, I think it will be
E
a skew.
minus.
Yes.
Yeah.
In this case, it will be a skew. But it will depend on the n and m. You will get different.
Right.
So the point is that we can develop a whole theory of star products, and then the star product will be graded commutative. And we can define the star product for all n and m, and also in order to define the star product, we don't need that the regulator is 0. Then it will be a more complicated formula because it will involve the theta of y, but one can define this star product. The point is that then the result will depend on the choice of gy and gz. So if we want some invariant that only depends on the cycle, we have to impose the regulator size. Okay, is there a biextension that can be related to this guy? So can we construct a biextension whose invariant is given by this integral that I just defined? Well, now the problem is that proper intersection, in this case, n plus m equals to 1, implies that the intersection of p1 star of y intersected with p2 star of z is not empty, but in this case it will be a finite set. It will be a bunch of points. So it can be non-empty, but it will be a bunch of points. Well, now in the next diagram, I will shorten the notation a little bit, and then I will write z twiddle will be just z multiplied by the square. Y twiddle will be y multiplied by this gm, and x twiddle will be x multiplied by this square and by gm, just because it didn't fit in the diagram. And also, one has to be careful that the next diagram is pretty but wrong, and the right diagram is much more complicated. So the problem here comes from the fact that I was saying before that the square and gm were in duality, because we can always look at x minus a relative to b, or x minus b relative to a. In order that these two objects are in duality, I need that a and b are in what is called local product situation. If they are arbitrary, it is not true that they are in duality. And so in the next diagram, in some sense, one needs to make some blow-ups on x twiddle so that all the objects are put in product situation. So it's not as easy and just considering x twiddle here. So one has to be careful and make some blow-ups to make things in product situation. But let's just, for the sake of simplicity, pretend that everything is nice. Now I have this big diagram, which is very much reminiscent of the diagram we had in the classical case. So here I have the cohomology of x twiddle complement of y, and here I have the cohomology of x twiddle relative to z. Here is the cohomology of x twiddle, here I have the cohomology with support on y twiddle, here I have the cohomology on z twiddle, and I complete the diagram as before. Okay? Now I can look at what happens in this diagram. For instance, now the problem is that this corner here is no longer 0. So this will be different from 0. And the bigger the intersection, the more complicated can be this diagram. Now, because here in this case, I also know that, this will be different from 0. Then it has the class of y. The class of y lives in this h2p plus 1 of x twiddle with support on y. And then someone will complain quickly saying, hey, the class of a cycle will live in some even cohomology, not in an odd cohomology. But recall that this x twiddle was x cross square cross gm. So and y lives on x cross square. Since I have multiplied everything by gm, this means that I have increased the degree by 1. So one has to think that h2p plus 1 of x twiddle is h2p of x cross square. And this is where the class really lives. So this is a class that lives here. And also, this class is not a map from z minus 2p, but is z minus 2p minus 1 because this gm induces an extra twist. Now here I have the h2p of x twiddle, but h2p of x twiddle, since I have multiplied by the square and the gm, this is really h2p minus 2 of x, and twisted by minus 1. because of the G. And here I have the cohomology of set, and I have the class of set. The fundamental class of set will give me a map from this guy to this Hodge structure. Again, the dimension of set is p minus 1. And the fact that this I have here taking h to p minus 1 is because I have this change of degree because now of the product of the square. Okay. So I have this diagram. Now, what can I do? I know that this guy here is different from 0. And in fact, one can see that this is exactly this pure Hodge theory to the power exactly the number of points on S. Because it lives in the exact spot where it is maximally non-trivial. Then I have here, I have made the let's say, yeah. So I made the push out with respect to this map to replace this class, so this group by this group here, and make these dots 0. So I have set of Q minus D. I have also twist everything by 1. Now, what I get here, I take the pull out by this class here. And then here I get the analog of the extension of Y. But now this will be an extension of higher degree. But this extension will give me exactly the regulator of Y. So the regulator of Y classifies this extension. Here I will get the dual of the extension of Z that also classifies this. But the point is that now this is non-trivial, and this is an extension that may be non-trivial. This is again an extension that may be non-trivial, and these are, in this case, these are Kummer extensions. So the jump is just by 1, and this will be an extension that will be classified by some logarithm of some quantities in this case. Okay. So what do we get at the end? So we get a mixed Hodge structure B here that is made out of these 4. So the pieces of this mixed Hodge structure are these 4 pieces here. So I have a cohomology of weight exactly 2p minus 2, pure of weight 2p minus 2, which is the cohomology of 2p minus 2 of x. I have a piece of a pure of weight 2q minus 2d, sorry, 2d minus 2q. I have a piece of weight exactly 2p, and I have also this piece that, observe that this piece has exactly the same weight as this piece.
So B is what, sorry, can you?
B is the codimension of Y.
Yeah, no, capital B is, you had in your previous diagram, you had a description of B, yeah.
Yes.
Okay, so that's roughly B.
Yes, exactly. No, yeah, the point is that,
Yeah,
so B is a subquotient of this guy here.
right, okay.
So the point is that here, the point is that this goes on here, and this can have a lot of other components. So I have the class of Y that is given by choosing some multiplicities of the components of Y, and then I take the pullback of this class. And also I have here the class of Z. This will give me a map from this guy to this guy, and I take the push out of this. And then whatever remains of this pullback and push out is the B here. So the B will be a subquotient of this guy here. Okay. So it's more or less very similar to what happens in the classical situation. In the classical situation, we also were considering the complement of Y relative to Z, and a subquotient, the B extension was a subquotient of this object. Okay. But the difference with the classical situation is that we still have this step. Okay. Now, once we take the push out, what we get is a mixed Hodge structure that now will have this shape. We'll have, so I twist everything to move the object that was in degree 2p minus 2, I move it to degree minus 2. And then this will be in degree 0, this will be in degree minus 4. Okay, so now the jump is in 2. So it's not a jump by 1, it's a jump by 2. So now the extension between this and this is no longer trivial, even over the real numbers. The extension between this and this is no longer trivial, even over the reals. And also I have this other piece. Okay, so this is the mixed Hodge structure. It will be of this. Now, what invariance can I define to this guy? So now to this sum, I will call it H here. This one has weight minus 2. And now I can play the same trick as I was using before. So I can take an integral generator of the piece of type 0, 0. And now I can look at x minus x bar. Now the problem is that this x minus x bar is no longer true that it will live in b minus 2 minus 2. So it will live in two weights below. So it will have some components here and it will have some components here. Now, the components here vanish because the components here really represents the regulator. And I am assuming that the regulator is 0. The components here will not vanish and will be given by some logarithm, but I can project to this component here. And this component here, the projection to this component here, will tell me exactly how split or non-split is the relation between the two extreme guys. Okay? So this will be the invariant of this Hodge structure going to these two extremes. Observe that this invariant can be defined regardless of the fact that the regulator is 0. I mean, I have my Hodge structure, and independently of the fact that the other invariants are 0 or not, I can always define this invariant. But of course, the Hain pairing I defined previously was only well defined when the regulator was 0. And then the theorem we have with Goswami and Pearlstein is that in the case when n and m is equal to 1, and assuming that the regulator of y and the regulator of z is 0, then there is a universal constant c. Here I say an universal constant because in all this business, you are forced to choose some normalization factors. And if you take different normalization factors, then you will get different things. So this constant is just, you can get this constant to be equal to 1 if you choose wisely your normalization factors, but the point is that in this case, the Hain pairing is exactly the invariant attached to this mixed Hodge structure. Now the point is that there are other higher Hain pairings. For instance, James Lewis has a definition of Hain pairing, but I think in his case is for cycles that are rationally equivalent to 0.
Yes, originally.
Yes, and then the objective now is to see whether it agrees with this Hain pairing or not. So it's the next.
You're better.
Yeah, better they agree because we don't want to have different Hain pairings with different notions. Okay, and then just end the things with an example to see what is the flavor of the objects we get. So now, what are more or less the simplest objects, the simplest higher cycles we can construct? Well, I can take my variety x to be a P2. Then on P2, I can look at O of 1, so the line bundle, the tautological line bundle, and I can take 3 global sections of O of 1. This will be just forms of degree 1. Then Li will be the divisor of Si. This will be just a line in P2. And then I take the function Fi will be just the function given by the other two sections. So if on the line Li, I take the function given by the other two sections. Here I am using mod 3 arithmetic. So 3 plus 1, 2 plus 1 will be, or 3 plus 1 will be 1. And then I take the points Pi will be just the intersection of these two lines. Now I can define a cycle associated with this S1, S2, and S3. That will be a cycle in this further normalized complex that is given in the next picture. So I expect that one can understand what is going on in this picture. So this is P2. And in this P2 I have these 3 lines, L1, L2, and L3. Now here I am picturing P2 times P1. This is the phase P2 times 0, and this is the phase P2 times infinity. Now over this line, I have this function Fi, which is defined on the line Li. Since I have a function, I can lift this line to x cos P1 with a slope given by the function. So the function will tell me what is the value on P1. Then this line I can also lift to this slanted line here, and to this line I can lift to this slanted line here. Now, this cycle is so this guy is a cycle in the usual cubical Chow complex, but it's not a cycle in the normal set complex because the intersection of this guy with this face is 3 points. The intersection of this guy with the other face is minus the same 3 points. Then if I add together, this will be 0. But if I want a cycle in the normalized complex, I have to add these vertical lines. Okay, these vertical lines with negative situation will just give something that intersecting with this face is 0, intersecting with this face is 0. And then I get really a nice cycle on this complex. Okay, now then I can take 3 sections, another 3 sections, and I look at them that are in general position. Then one start making computations and computations, and then fortunately all integrals can be made explicitly, and the result will be that this Hain pairing will be given by a linear combination of the logarithms of the Bloch being the logarithm and products of logarithms, and this will be the Hain pairing we obtain in this case n equal to m equal to 1. Okay, thank you very much for your attention.
So any questions?
Yeah, one thing I'm thinking about here is, have you thought about the situation of degenerations, a semi-stable degeneration to a little rational curve across a surface, let's say?
Yes, so this is
Look at your resulting elevator
Yes.
effect on the biextension.
so this is the dream, one of the dreams we have, in the sense that, so for instance, there is this famous degeneration that if one takes the Ceresa cycle in an abelian variety of genus 3, and then we make the genus 3 curve degenerate to a genus 2 curve, then the abelian variety will degenerate to this abelian variety times a torus. And then if one looks how the Ceresa cycle degenerates, it will give us a higher cycle, but on an abelian variety of dimension 1 less. And then I think it was Colombo, maybe, that studied how the regulator of the Ceresa cycle degenerates, and then the asymptotics is dictated by the regulator of this collinear cycle. And we would like to be able to do something similar in the Hain pairing. So take 2 cycles and degenerate them in a similar way. But the problem is that now here we need 2 cycles that lives in different spaces. So it's not clear what objects, how to degenerate them and how it fits in the picture. So this is for the moment just a dream we have not, but we have not been able to. But we would like to see some degenerations of this.
So you have a remark when in the beginning. So you said when the x, y, z is defined over the Q,
Yes.
then you can have some finite component.
This was in the classical thing, in the classical theory. So here we really do not know what to do with integral coefficients, because the Bloch group, okay, you can define them, but they have nice properties when you work over fields, and over rings, things gets much more complicated. So I don't know how to make an intersection product between hierarchical groups over rings, for instance. And the second point is that, so in some sense, there is a big difference between the classical case and this case, because if you look at the Heidegger K-theory of number fields and of the ring of integrals of number fields, if you look at K1, they are very different, because you have all the units of the field that are not units of the ring. Hence, if you look at where the Hain pairing lands, it makes a very big difference. So the Hain pairing is related to the K1. It makes a very big difference if you are looking at the field or you are looking at the ring of integrals. But if you look at Heidegger K-theory, the Heidegger K-theory of the number field and the Heidegger K-theory of the ring of integrals of the number field are equal up to torsion. So you will not see any difference on the Hain pairing when you look at the integral part or not. So I will say that. So my guess is that once one is able to define the arithmetic components, the components over things, all the defined components will be torsion of these kind of things. Is my guess, but I have no idea how to do it. So maybe this is just an excuse for not to do it.
So the obvious question is, can you make this motivic? I mean, in some sense, you did, but you rapidly went to the Hodge world.
Yes.
I would be tempted to try to stay in the motivic world for a little while longer. I mean, if you think of the most classical case, where you have points on a curve, you have 2 disjoint 0 cycles, degree 0, then what you're really looking at so fix one of them, or fix both of them, in fact. And then, but look at one, and you look at all ways to move it rationally. And that's a torsor.
Yes.
Under basically the group of rational functions.
Yes.
So then the point is that you can pair that group of rational functions with the other zero cycles by evaluation. And that will make sense because you assume that the polar loci are disjoint. So that gives you then push out your torsor is the collection of possible rational functions, but you push it out by this evaluation to get a GM torsor. So it would seem that the natural thing to do would be to try to emulate something like that, to try to understand the torsor.
So this is interesting in the sense that here I am constructing the hypering, which in some sense is related with the real Deligne homology. Now, if we go back to the case of curves, so if now I look at an elliptic curve, I don't need that my cycles are rationally equivalent to zero. I only need that they are homologically equivalent to zero. So on P1 there is no difference, but on the elliptic curve, this makes a difference. Now, if they are homologically equivalent to zero, I can get a well-defined class on real Deligne homology. But if they are rationally equivalent to zero, then I can get a finite class motivically, and then a class in integral Deligne homology. So the point will be, if one wants to try to lift everything instead of looking at real structures, we look really at integral structures, then we will need a stronger condition that it is rationally equivalent to zero in order to
No.
I think so.
You don't. What you're looking at is the torsor. You don't care about the cycle you started with.
Yes.
The torsor is rational equivalence. So that's the same. I mean, you're not really moving the cycles; they stay fixed.
Yeah.
You're moving possible
representatives of the cycle.
Right.
Yes.
Possible representatives of the cycle.
Okay.
And so that you can evaluate at the other points, irrespective of anything. So I don't need to assume my cycles or anything about my cycles. Maybe degree zero or something, so that I don't, when I evaluate, I don't get the constants coming in. It's confusing because it's somehow it's the torsor that's playing the role. It's not the base.
Okay. Yeah. I see. Yeah.
Any other questions? Okay, we thank the speaker.